Hi, this is Dr. Xu, teaching mine ventilation for mining engineering. In this video, we will practice solving a hard rock mine ventilation network. I have uploaded a PDF file with the question, which you can download, print it out, and make notes on it. Let's have a look at the question. Air is to be delivered to an ore body via a surface decline 1 to 3 here, and intake hoisting shaft 1 to 2 here. The dimension of these two airways are also given, but in this problem we do not need these dimensions as the airways resistance are given on the diagram here and here. Air enters the ore body from the intake shaft 2 to 3 via two haulage levels. So from 2 to 3, there are two haulage levels. One is here, one is here. And their parameters are given as 5 meter wide by 5 meter high, 500 meter long, and have a K factor of 0.009. Air passes through the ore body via several airways, 3 to 4, here to here. As the total resistance for 3 to 4 is given, we don't need to know the exact layout in the ore body and can treat airway 3 to 4 as a single airway. After passing the ore body, air is exhausted through the exhaust shaft with resistance of 0.015 from 4 to 5. An exhaust fan is fitted on the top of the exhaust shaft, pulling 326 cubic meter per second of air at the speed of 500 RPM. There is no control over the distribution of air between the decline and intake shaft. This means there is no other regulators, and the provided resistance in the intake shaft and decline are the actual values. Let's redraw this ventilation network and simplify it. So from the surface, from 1, it goes to 2. Here, that's the shaft. And from the shaft, there are two levels, goes to 3. The top level and the bottom level. And from 1 to 3, that's the decline. And from 3 to 4, that passes the ore body. And from 4 to 5, that goes to the surface fan. Okay, as we can see, airway 2 to 3, there are two identical airways in parallel, and they are in series with 1 to 2. Altogether, they are in parallel with 1 to 3. And the rest part of the airway, they are in series. Now let's look at the question. Question 1 asks us to calculate the resistance of the airway for one haulage level. There are two haulage levels here and here. And they have the same parameters, so they are identical. Since the friction factor is given for the haulage levels, we can use the Atkinson's equation to calculate its resistance. So, question 1. The resistance for one haulage level, equals to, if you recall the Atkinson's equation, it's KCl divided by A cube by rho divided by 1.2 equals, K is given. K is 0.009 by C. So the dimension of the haulage level is 5 meter wide by 5 meter high. So C is 5 by 4. L is 500 meters divided by the cross-sectional area, that's 5 by 5 cube by rho divided by 1.2, and rho is given as 1.25 divided by 1.2 equals to 0.006. Question 2 asks us to calculate the total resistance of the two haulage levels. As we know that the two haulage levels are identical and in parallel, we can use the equivalent resistance equation for parallel airways. Question 2. So resistance for 2 to 3 equals to, can use the equation square 1 divided by square root of R1 haulage level plus 1 divided by square root of R1 haulage level. This is calculated in problem 1. If you plug in the number equals to 0.0015, so this equals to 0.006, this equals to 0.006. Question 3 asks the total resistance of the intake shaft and haulage levels. As they are in series, the total resistance is just the sum of each individual resistance. As we can see here, the resistance from 2 to 3 is just calculated from problem 2. That's 0.0015. Therefore, the resistance of the intake shaft and haulage levels, that's the total resistance from 1 to 2 and to 3. So the third question, the resistance R 1 to 2 to 3 equals to R1 to 2 plus R2 to 3 equals to R1 to 2 is given here. So that's 0.0076 plus 0.0015 equals to 0.0091. Question 4 asks the total resistance of airway 1, 2, 3 and 1, 2, 3 in parallel. So that's the total resistance of this part. As we can see, they are in parallel. We can use the same equivalent resistance equation for parallel airways. Question 4, the resistance 1 to 3 total equals to square 1 divided by square root of resistance of 1 to 3 plus 1 divided by the resistance of 1 to 3 equals to 1 divided by square root of 0.0091 plus 1 divided by square root of 0.04 square equals to 0.00417. Question 5. How much air is in the intake hoisting shaft, each haulage level, and how much in the decline? Using the quantity divider rule, we can calculate how much air goes to airway 1 to 3. Let's go back to this drawing. There are 326 cubic meter per second of air come out from the mine. Therefore, the total air come in from 1 is 326 cubic meter per second as well. As we know, airway 1, 2, and together with 2, 3, they are in parallel with airway 1 to 3. Here, we can use quantity divider rule to calculate how much air goes to airway 1, 2, 3.
Question 5.
Quantity goes to 1, 2, 3 equals to the total amount of air goes to node 1, 326, by the total resistance R1, 2, 3. That's the total. Okay, so that's the resistance of this whole part we have calculated in question 4, divided by resistance 1, 2, 3. So that's the resistance from here to here. That's the total. We have calculated that in question 3. So if we plug in the number 0.00417 divided by 0.0091 equals to 220.68 cubic meter per second. So there are 220.68 cubic meter per second of air goes to 1 to 2 and 2 to 3. That's the total air goes to 2 to 3. They are going to be distributed among the two haulage levels. Since we know the two haulage levels are identical and has the same resistance, half of the airway will go to each haulage level. So Q1 haulage level equals to 220.68 divided by 2 equals to 110.34 cubic meter per second. The last quantity we need to solve is from 1 to 3. So we know there is 326 coming into node 1, 220.68 coming out from node 1, and the rest has to come out from 1 to 3. So quantity from 1 to 3 equals to 326 minus 220.68 equals to 105.32 cubic meter per second. For calculating the quantity flowing into 1 to 3, you can also use the quantity divider rule to calculate and get the same answer. So you can use this equation Q1 to 3 equals to 326 by square root of the resistance 1 to 3 total divided by, so this total is total resistance of this whole part divided by the resistance 1 to 3. You will get the same answer. Question 6. Calculate the total resistance of the mine and the surface fan static pressure. So the total resistance of the mine is the resistance of this part plus resistance from 3 to 4 and 4 to 5 because the rest part is in series. So R total, so that's the mine total resistance, equals to R1 to 3, that's the total, plus R3 to 4, plus R4 to 5. R1 to 3 total, we have calculated 0.00417 plus R3 to 4 is given 0.0014 plus resistance 4 to 5 is given 0.015 equals to 0.02057. So using the very important square law P equals to RQ square, the surface fan operating static pressure is P equals to RQ square. This is the total equals to 0.02057 by 326 square equals to 2186.1 Pascal. Question 7. Demonstrate using a sketch that Kirchhoff's second law, the pressure balance law, is obeyed for your solution in the mesh 1 to 3 to 4 to 5 and to 1. So from here, 1 to 3 to 4 to 5 and back to 1. Let's draw the sketch. We have 1 here. That's the decline, goes to 3. 3 goes to 4. 4 goes to 5. Remember there is a little fan here. And the flow direction is like this. Node 5 and 1 can be treated as virtually connected as there is no pressure drop on the surface. So they are virtually connected. There's no pressure drop. If I define the clockwise direction is the positive direction, so I define this direction is the positive direction. Kirchhoff's second law says negative pressure loss from 1 to 3 because the flow direction is different than my defined positive direction. That's why there is a negative sign here. plus negative pressure drop from 3 to 4. The same reason, it's the flow direction is different than my defined direction, plus negative pressure drop 4 to 5. And remember, there is a fan. The fan flow direction is also that way. So plus the fan flow direction is also opposite to my defined positive direction. That's one negative sign there. And the fan provide a pressure rise, which can be treated as a negative pressure drop. So negative pressure drop of fan plus negative pressure drop from 5 to 1 equals to 0. We know pressure drop from 5 to 1, well, 5 to 1, they are on the surface. The pressure are all atmosphere pressure. There is no pressure drop, so this equals to 0. And the fan pressure has been calculated in question 6. So this is given equals to 2186.1 Pascal. Minus become positive. So rearrange it. Plus 2186.1 equals to 0. Pressure drop 1 to 3 equals to R1 to 3 Q1 to 3 equals to R1 to 3 is given 0.04. Q1 to 3 has been calculated in question 5, that is 105.32 square equals to 443.69 Pascal. Pressure from 3 to 4 equals to R 3 to 4 Q 3 to 4 equals to R is given. It's 0.0014. Q, as we can see here, 326 cubic meter per second of air come out from here, and this is in series with the exhaust shaft. So the same amount of air, 326 cubic meter per second of air, passes through 3 to 4. 326 square equals to 148.79 Pascal. Pressure drop 4 to 5 equals to resistance 4 to 5 Q 4 to 5 square. Oh, sorry, here is square, here's square. Equals to the resistance 4 to 5 is given 0.015 by 326 square equals to 1594.14 Pascal. If we plug in all these numbers to this equation, that is negative 443.69 minus 148.79 minus 1594.14 plus 2186.1. If we do the calculation, that equals to negative 0.52 Pascal. But Kirchhoff's second law says the result is supposed to be 0. Here, this little residue is due to round-off error. Therefore, this verifies that Kirchhoff's second law holds in the circuit 1 to 3 to 4 to 5 and back to 1. The pressure drop in this closed circuit equals to 0. Question 8. The surface fan speed is increased from 500 to 600 RPM. What will be the fan's new operating point? We can use the fan laws to solve this question. So the new quantity Q at 600 RPM divided by Q at 500 RPM equals to 600 divided by 500. Therefore, Q 600 divided by, at 500 RPM, the quantity is 326 equals to 6 divided by 5. Q 600 equals to, therefore, we solve Q 600 that equals to 391.2 cubic meter per second. For pressure at 600 RPM divided by pressure at 500 RPM equals to 600 divided by 500 square. So pressure at 600 RPM divided by the pressure at 500 RPM, we have calculated it, and it is in question 6. That's 2186.1 Pascal equals to 6 divided by 5 square. We can solve pressure 600, that equals to 3147.98 Pascal. Therefore, after increasing the speed, the fan's operating point is quantity is 391.2 cubic meter per second, and the pressure is 3147.98 Pascal. That is all for this tutorial. Hopefully you have understood it. This is Dr. Guangxu. Thanks for watching. I will see you in the next video.